Welcome to this video number 2 on the topic waves. Here we'll be solving IGCSE past paper questions. In the previous video 1, we have already done 3 questions, question 1, 2 and 3. In this video, which is second video, we'll be taking up 3 more questions named question 4, 5 and 6. So let us start with question number 4. Question number 4, the A part asks you, state how a longitudinal wave differs from the transverse wave. It's a 2-mark question. So 2 valid points if you can make out in your answer. Please refer to my video on longitudinal and transverse wave to understand how the question for these are written. So longitudinal waves, how do you define? The transverse wave, how do you define? Okay. So vibration is parallel to the direction of the travel, or compressions move in the direction of the travel. It's a 2-mark question. So one of the marks for these things, or if you just write variation, it is a vibration, compression, refraction, you'll get 1 mark. So let me explain you what the mark scheme is telling you about how the marking for this question is done. If you are just saying in your answer that a longitudinal wave contains compression and rarefaction, if you're just making this point, you'll not get all the 2 marks, you'll just get 1 mark, right? Another thing what the question paper, the mark scheme is saying is that if you're writing that in longitudinal wave, the direction of vibrations are parallel to the direction of wave travel. If you are mentioning this statement, you'll get whole 2 marks. Full 2 marks. If you are just stating this statement which I am putting in brackets, you get full 2 marks because that's a more mature definition of longitudinal wave. If you are just mentioning compressions and rarefaction, you'll just get 1 mark. If you are mentioning both the points, you still get 2 marks, nothing more than that. So the correct definition of longitudinal wave is, as is explained in my video, it is connecting the phrase 1 and the phrase 2, which is direction of vibrations of the medium are parallel to the direction of the wave travel. Practice it more and more, very relevant, and this question comes in the examination so many times. Let's come to the B part. A sound wave of the frequency 7.5 kilohertz travels through a steel beam at a speed is also given 61,000 meters per second. Calculate the wavelength of the sound wave in the steel beam. So I would highly recommend that before we start the question, you should pause the screen, answer the question and play the question again to look at the solution to tally your working. If there is any mistakes, you'll identify them and you'll know how to write the correct answers. So there is only one equation in the chapter waves. Trust it, go by it, write the formula. So what is that one equation? V is equal to F lambda. They are telling you to find lambda. So lambda is V over F. You're given the value of V, 6100 over frequency, which is 7.5 times 10 to the power 3. It's kilohertz. Divide these two numbers, you'll get your answer. Let's look at the mark scheme. Sorry, this is the mark scheme. They have done the same exact thing and it should give you your answer. That should be approximately this much. In meters or in millimeters, this much. So let us take up 0.81 from the mark scheme. The answer when you divide these two numbers is 0.81 meters. Now the next part. The sound wave passes from the end of the beam into air, right? Sound is traveling from the solid to the air. State the effect on the speed of the sound. Where is the speed of the sound faster? In a high density region. When the sound is moving into the air, air is low density. Density is going down. Density is going down. So what happens to the speed? Speed goes down. Right? This is something that we have already discussed, that if the particles of the medium are compact, close together, the sound travels faster in those mediums because it is easy for the vibrations to travel in such solid and compact medium. Whereas when the density is less, the speed goes less for the air. And these things are very well explained in the chapter sound. Please go through the chapter sound to understand about the speed of the sound in solid, liquid and gases. What is the effect on the wavelength of the sound? Wavelength. Now these things, whenever the speed is linked with the wavelength, you have to use the wave equation. V is equal to F lambda. I have already several times told you in the theory as well that the frequency is a constant for any wave. Frequency does not change. Frequency does not change. We know that the speed is going down. If the speed is going down, the wavelength also has to go down so that the left hand side remains equal to the right hand side. Frequency is a constant. To maintain the wave equation true, because frequency is constant, whenever the speed goes down, the wavelength of the same waves go down so that the left hand side remains equal to the right hand side. Let us look at the mark scheme. The speed decreases, the wavelength decreases. That's what they are looking for. They are not asking you for any explanation. It's a 1 mark question. Even if you just say that the wavelength goes down, you get full marks. They are not asking for the explanation, but some questions do ask for the explanation, as we have seen in video number 1, where we worked out some solved examples. Right? So let us come to the next question, which is your question number 5. You may pause the video, solve the question, play it again to look at the working. So let us start with the part A. In the figure shows an aerial view of the wavefront passing from an open sea into the outer harbor. So waves are coming from the sea and coming into the harbor region. You want to maintain some calm waves near the shore. So you put some barriers so that the wavefronts which are coming from the sea, they calm down, they are under control. So you see 2 barriers being put, one barrier and then the second barrier. The wavefronts and the outer wavefronts are curving at the end. If you see, there is a curve at the end. Name the process that is occurring at the entrance to the harbor. What is this curving process called? It's a 1 mark question. Just give the name. Diffraction. Easy question. Let us come to the second part. On the figure, carefully complete the wave pattern on the wavefront as the wavefront progress through the outer harbor. As the wavefront are progressing towards the outer harbor and the inner harbor, show the rest of the wave pattern in the outer harbor and 3 wavefronts in the inner harbor. So there is some space here. You have to draw some wavefronts here. That's what the question is saying. And you have to draw some wavefronts here. So let us complete it. It's easy. Make sure that you're not changing the wavelength. I'm sorry. Drawing straight line on the screen can get a little tricky at times. Let me curve it at the end. Like this. I can fit just one more wavefront here. Okay, now some more set of wavefronts. New diffraction happening on the other inner harbor. Right, at least 3 they are saying. 3 wavefronts in the inner harbor. So that's how your question is done. If you see that the spacing between the wavefront is not changing, there is a slight error here on my part, you can rectify it, make sure it's not happening in your answers. I am working on the screen, so working is slightly difficult, but in your notebooks you can always use erasers and rectify your answers. The spacing between the wavefront is nowhere changing. Nowhere changing. Why? Because the wavelength does not change in diffraction process. Let us come to the next question. On the figure shows an aerial view. So this first part was on diffraction. Looks like that the second part is coming on some other concept. Looks like it is on refraction. Shows an aerial view of wavefront in deep water approaching a region of shallow water as they travel, where they travel more slowly. So speed here is high, V stands for speed. Speed here is low. This is a theory which is very well traveled on the topic video on refraction and reflection. Please go through it, how the wavefronts behave when they move from deeper to shallow region, very carefully and very precisely discussed in that video. The speed is high in deep water, speed is low in shallow water. The depth is high here, so speed is high. The depth is low here, speed is low. Name the process. Now again they are telling you to name the process. It is a 1 mark question. As the wavefront passes from deep to the shallow region, you say refraction. It is refraction. Complete this figure to show possible position of the 5 wavefronts in the shallow water. They will be bending towards the barrier. Let me use the black ink. I do not have the option for the black ink. So they will be bending towards the barrier. Bend them towards the barrier like this. Each of the wavefronts, you can bend each of the wavefronts towards the barrier. Bending means the angle with the barrier is going down. If this is your angle theta 1, theta 2, the opposite angles we are talking about, the new angle theta 2 is less than theta 1. It is bending towards the barrier. It's a 2 mark questions. It is a 2 mark question. You'll get 2 marks when the examiner will see all the 3 wavefronts and if they are bent in the correct direction. Let us look at the mark scheme to understand it well. At least 3 parallel straight wavefronts join to the original wavefront. At least 3 straight wavefronts sloping down to the right or constantly reduced at a constant reduced wavelength. If you see what is happening to the spacing between the wavefront, spacing between the wavefront here was high. Let's call it lambda 1. The spacing between the wavefronts, which is the wavelength, has gone down, lambda 2. If you see, lambda 2 is less than lambda 1. So what do you see? Depth has gone down, speed has gone down, the theta angle has gone down at the shallow region. These are your theta angles. It has gone down. Even the wavelength has gone down. Everything has gone down. Whenever the depth goes down, the speed goes down, the theta angle with the barrier goes down, the wavelength, as you can visually see, it has gone down. The wavefronts are close together as compared to as they were earlier before. Alright, so this was a very nice question on refraction. Let us move on to our question number 6. You may pause the video here, solve the question yourself, come back and play the video again. So talking about question number 6, it shows a surface of water in a tank. Alright, and diffraction is happening, as you can see, but one more process is happening, looks like. Let us understand the question. A straight wavefront are produced on the left hand of the tank and travel towards a gap in the barrier. curved wavefronts travel away from the cap. Name the process that causes the waves to spread out at the cap. 1 mark question, you have to just name the process. It is, you said it correct, it is diffraction. Second question, suggest a cause for the reduced speed of the wavefront to the right of the barrier. They are saying here, which is the right side. They are saying that the speed has gone down, right? Reduced spacing. Reduced spacing. The question is saying, suggest a cause for the reduced spacing of the wavefront. I'm sorry, I read the question wrongly. They are saying that the wavelength has gone down, reduced spacing of the wavefront towards the right. Here the spacing, if you see, is lesser as compared to the spacing earlier. Spacing between the wavefront is lambda. What has gone down? Lambda has gone down. Lambda goes down when the speed goes down. Speed goes down when the depth goes down. Right? So what is happening on the right side? You can either say that the depth has gone down, or you can say that the speed has gone down. You can go through my video on reflection and refraction. The refraction of water wavefronts is very nicely explained, and all this relation between lambda, speed, depth and the angle of bending towards the barrier, everything is properly explained. Right, let us look at the answer with the mark scheme. The process is called diffraction. You can say the wave travels slower. Either you talk about the speed, the wave speed has gone down, or you can say that the water is shallow. Depth has gone down, which is same as shallow. Alright, next part. State how the pattern of the wavefront to the right of the barrier changes when the gap is made narrow. When you're making the gap here, this gap they are talking about, when you're making it more narrow, this is a property of diffraction. Narrower is the gap, more is the diffraction. So more diffraction. We have a video on diffraction as well. Please go through it to understand the answer for the part 3. Let us come to the part B. It shows a wave traveling in the direction of the arrow along a rope. You are creating some rope. Explain why the wave shown is described as a transverse wave. How do you define transverse wave? You say that the oscillation of the medium is perpendicular to the direction of wave travel. Alright, because they are perpendicular. Take any point on the wave. How is that point moving? Up and down. Whereas how is the wave progressing? Like this. If you look at the angle between them, it is 90 degrees. Let us tally the answer. Oscillations are up and down motion. It is at right angle to the direction of the wave. Or you can say that the motion of the rope or the particle is at right angle. Right angle is the key term to the direction of the wave. This is a very common and easy question that comes again and again. How to define transverse wave and longitudinal wave. Please go through these videos on transverse and longitudinal wave to understand how the two key phrases of these definitions are connected. Okay, the next part, the speed of the wave along the rope is given to you. Calculate the frequency of the wave. How do you calculate the frequency? What do you think you have to do? You have to know just one formula for waves chapter, V is equal to F lambda. They are telling you to find the frequency. Frequency is V over lambda. V, which is velocity, is given to you 3.2 meters per second. But what about lambda? Is lambda given to you? Is lambda given to you anywhere in the question? Think about it yourself. Look about the data which is given. 2 times the wavelength. This is your lambda and lambda. You are given 2 lambda. 2 lambda is 2.4. So lambda is how much? 1.2 meters. So you write down 1.2 here. Divide these two numbers and you will get your frequency. Let us see if we are doing it correctly. Yes. Same thing we have done. Exactly the same thing. Lambda is 2.4 over 2, 1.2. So frequency is 3.2 over 1.2. This correct completes your answer, or there is another way of doing it. If you are doing it this way, you can tell your answer this way. We are doing it in this way. Answer is 2.7 Hertz. 2.7 Hertz. If you look at it, it's a 3-mark question. If you're writing your steps properly for each of the steps, you'll get 1 mark. 1 mark for writing the formula, 1 mark for substituting the correct values in the formula, and the last 1 mark for getting your answer correctly. If you're not writing your steps, and still your answer is correct, if your answer is correct, this is a catch here. If your answer is 2.7 Hertz, answer is correct, you get full 3 marks. But if your answer is wrong and the steps are also not there, you get 0 marks. That's why it's an important habit to write the formulas, write the steps, so that if finally your answer is also wrong, you'll not get straight 0 marks. You'll still get some marks on your steps and your working. So here is the mark scheme. You can look at the mark scheme, take a snapshot of it, and solve this question again. We have finished our video number 2 and 1. Next video, which is video number 3, will be on question number 7, 8 and 9. Thank you.